In this video, we'll take a look at the sampling distribution of a proportion. We'll look at key symbols, main characteristics, and assumptions and conditions. The population proportion is represented by a lowercase p. It's the parameter of the model for proportions. The theoretical model of all possible sample proportions is given by the symbol p hat. You might see it written as p dash hat, or you may see a symbol that looks like this. There are three characteristics of a sampling distribution of a proportion. First, sample proportions appear to be normally distributed. That is, their distribution is unimodal, symmetric. Next, the distribution of the sample proportions appears to center at the population proportion. Thirdly, the standard deviation of the sample proportions is found by the standard deviation for p hat being equivalent to the square root of p times 1 minus p divided by n. Written more concisely, the standard deviation for p hat is equal to the square root of p, the probability of success, times q, the probability of failure, divided by our sample size, n. When working with sampling distributions for proportions, certain assumptions and conditions must be satisfied. Independence. The sampled values must be independent of each other. That's our first condition. Next, our sample size assumption. That is, our sample size n must be large enough. Next is randomization. Subjects should be randomly assigned or come from a simple random sample. Then we have our 10% condition, which states that our sample size, n, should be no larger than 10% of the population. Finally, our success-failure condition. That is, sample size should be large enough to accommodate at least 10 successes and 10 failures. The number of successes and failures are determined by the following formulas. N, our sample size, times p, the probability of success, must be greater than or equal to 10, and n, our sample size, times q, the probability of failure, must also be greater than or equal to 10. Let's look at an example that requires us to use sampling distribution of a proportion. About 82% of all female heart transplant patients will survive for at least 3 years following the transplant. 70 female heart transplant recipients are randomly selected. What is the probability that the sample proportion surviving for less than 3 years will be below 71%? First, let's identify p and p hat. It says here that about 82% of all female heart transplant recipients. So this is our population proportion right here. In general, in the overall population, about 82% of these female heart transplant patients will survive for at least 3 years. P equals 0.82. If you're given a percentage, when you're doing your calculations, it's always best to convert to a decimal. Then at the end of the problem, if you'd like to convert back to a percentage, that's fairly easy to do. Just multiply your decimal by 100, or move your decimal 2 places to the right. Now let's identify p hat, our theoretical model of all possible sample proportions. P hat is 71%. This is our sample proportion. We want to find the probability, or p-value, of the sample proportion. To do so, we need three things. We need p, p-hat, and also the standard deviation of p-hat. To find the standard deviation of p-hat, we need to apply the formula. Standard deviation of p-hat is equal to p times q divided by n. So in our case, we'll say the square root of 0.82 times the complement to p. Now, because the sum of all probabilities in a sample space is always 1, if p is 0.82, then q must be 0.18, because 0.82 plus 0.18 gives us a sum of 1. I need to divide this by my sample size, n. If I look back at the problem, I see that my sample size is 70. So that goes right here. Now I simply calculate my values and obtain a result of 0.0459. Again, it's best to leave this in decimal form until the end of the problem. Keeping in mind our goal that we want to find the probability or p-value of the sample proportion, we need to use the information we have to find the z-score associated with our p-hat value, 0.71. The formula for finding the z-score is z equals sample proportion p-hat minus population proportion p divided by our standard deviation for p-hat. If we plug our values in, we get 0.71 minus 0.82 divided by 0.0459. This gives me a z-score value of approximately negative 2.40. What this means that assuming our sample proportion is normally distributed, the distribution of the sample proportion is centered at the population proportion, p. What is the probability that the sample proportion of female heart transplant patients surviving for less than 3 years will be less than 71%? Because the z-score that we obtained was negative 2.40, this is where 0.71, our p-hat value, will go. We're interested in finding the value of this region here. In other words, what is the probability or percentage that falls below a z-score of negative 2.40? To determine the probability, you can use either a standard z-score table or we can use a graphing calculator. I'll use a graphing calculator. In the graphing calculator, you'll type in the following commands. Second key, distribution, which is above the variables key. Then select normal CDF, which is option 2. Because we're interested in finding the probability at the left end of our normal distribution, we'll put in a lower bound. I like to use negative 100, but you can use any value from negative 5 and below. Anyway, I type in negative 100, comma, and then my z-score as my upper bound. Press enter, and it turns out that my probability will be 0.0082, or 0.82% if I convert to a percentage. As you can see, it's extremely unlikely that the probability of the sample proportion of female heart transplant patients surviving for less than 3 years is below 71%. In other words, we can anticipate that it will be significantly higher than that. In our next video, we'll take a look at sampling distribution of the mean.